Hello everyone. In this video, we are going to look at the theory of brush DC motors, and then in one of my future videos, I'm gonna basically run the DC motor with an Arduino code. But before I do the practical part, I want you to know a little bit about DC motors and then also later edge bridges and so on. So we know behind the scenes the theory behind before we move on to running a DC motor. And as I mentioned, most of the material I have here and in some of the other videos, they are coming from this amazing book, Introduction to Mechatronics Design by J. Carrier, if I'm not mispronouncing his name, hopefully. Carrier, I guess, and his colleagues. So there is more than one author on this book. It's a very, very good book on mechatronics, and it's really something great to have. So a brush DC motor is kind of the most common DC motor that you have seen in many places in real life, in toys, in household, small furnitures, and so on, probably, right? Because that's the least expensive one, the easiest to use, and of course the most popular one. Now it has disadvantages, which we're going to talk about, but this is kind of the most common one that you see in lots of different places. Now I don't want to talk a ton about inside of it, but inside of it, if you look, there is the permanent magnet called the stator, because it's a static, it doesn't rotate. There are these windings, armature, which is called rotor. So around these basically metal cores, you have windings that the electricity passes through them and converts them into magnets. And then we have basically a brush, which is going to be pressed against these what we call commutators with the force of the springs. And then, of course, there are terminals for the voltage, the current to come through. And, of course, there is the shaft that is spinning. So the main principle is basically two magnetic fields are repelling each other. So if I have the stator here having basically something like north up and south down, so this is from the stator, and the rotor has something similar, right? So it has basically the north up here and south up here. Clearly, the two north and the two south will repel each other. And because of that, there will be some torque and it starts moving. The problem is when this one rotates for 100, and here is a simple structure that you only have basically one set of poles, right, on stator and one on rotor. In most DC motors, you have several of these. But let's say, just to make it simple, you have one on the stator, one on the rotor. The problem is when it rotates 180 degrees, the north will come down and the south will go up. Now there is pure attraction between these opposite poles, and this is where it's going to stop rotating. Okay, it's going to be locked in place. So now you have to have a way to again switch these poles, force this S to be N and force this N to be S. So again, the repelling continues and this continuous rotation is achieved. So the way that you convert this S to N and N to S after 180, in this case rotation, is through this commutator, okay, and the brush. So the electricity is coming through the brushes, and then through this conductive, most of the time copper material, is going to go to these windings, to these coils, to the rotor, okay, because of the contact that the brush has with the commutator, and that is done through the force of the spring pressing the brush against the commutator. Now, when it rotates, the current that was coming through the brush, through the pieces of the commutator to the coil, the thing is the next commutator, these commutators are attached, basically each one of them, to one of these coils. So when the coil rotates, that piece of the commutator will also rotate with it. So commutator is not one single basically copper ring. It's not like that. It has pieces. So what you will see for a commutator, and if we want to go simple like that, at least in this case, we can say that there are at least two pieces, two kind of half circles, two bushings you might want to call, right? So something like this, and this is that brush that is in contact with it, and because of the contact, the current goes through. Remember, this was in this case N, this was S. Now when this one that is attached to this coil is rotating, it goes up, and this one comes down. The thing is, the direction of the current flow through the coil is going to be reversed. So in this case, let's say it is like this, okay, right? But when it goes up, the current in this coil is going to be backwards. So if right now is clockwise, when it comes up here, okay, let me use a different color. When it comes up there in this place, it is going to be backwards. It is going to go like this. It is going to go counterclockwise in this one, and in the other one reverses. So since the direction of the current in the coil is inverted, correct, the direction of north and south pole are inverted, and we know that from our electricity knowledge, that the direction of north-south depends on the direction of current flow through this loop, through the coil. So this is the mechanism for keeping constant rotation. Now, or switching the direction of the magnetic poles. Now, the brushes are typically made of low friction material. Like what? Like the graphite or some specific metals like platinum. The reason is because the spring is pressing the brush against the commutator, there is friction always between them. And if the brush is not made of low, basically, or friction resistant material, very fast you're going to see your brushes are going to go through lots of wear and tear. And the same thing can happen to the commutators, and you have to replace them very fast. So these are what we call sacrificial components. And these are the place of failure for most of the DC motors. Most likely when they fail is because the brush or the commutator or both are worn out. Now, as I said, many commutators are typically made of coppers or copper alloys, but brushes typically made of graphite or platinum. So, first of all, they have some weak links that will fail. That's one of their disadvantages. The other one, because there is friction, there will be some noise. This friction will cause noise, and it will cause electromagnetic interference or EMI, and it will waste some portion of the generated torque to overcome this friction. So they are not super efficient because of this mechanical friction. And there is one more thing that is called the brush bounce. Let's talk about that briefly. So remember, here we have a spring that is pressing the brush against the commutator. And so there is no contact here, okay? When you are pressing it, depending on how fast this thing is spinning and how hard you are pressing against it, okay, it could bounce back and you could lose connection for a short period of time, very short, and that is called the brush bounce. So you're going to get some vibrations because there is a spring in this system. So as I said, when the commutator or the rotor spins faster and faster, ultimately you're going to get to the place that you're going to get brush bounce, and you're going to get some resonance in the vibrations. So the brush cannot follow the contour of the commutator and stay in good contact. Okay? For that reason, the maximum speed that the rotor, or in general the motor, can spin is going to be limited. Because if you're going to go super fast now, this brush is going to bounce back and you're going to lose the connection. And when you lose the connection, there will be no magnetic field and there will be no torque. So the motor cannot operate. So you see, friction and the brush bounce are the two things that would limit how fast these motors can spin, and also how much torque they can generate because of a lot of losses in friction. Plus, they of course add noise, they add electromagnetic interference, and they have to be replaced. Their weak components have to be replaced quite often. So now that we know some very basics about them, let's look at the equations. So that was the mechanical component, but if you look at the electric circuit of it, so you have some voltage source that flows through the winding, and the winding, they have resistance and they have inductance. And because of the Lenz's law that you know, there is also some back EMF generated inside these electric circuits. Now, in the modeling that I'm using here, we are going to neglect the inductance, okay? Because inductance is typically much, much smaller than the resistance. Otherwise, this first equation that we're going to discuss, we have to add an extra term to it. So if we write the Kirchhoff's voltage law, or the loop, then voltage of the source is going to be equal to the component that is wasted in the resistance IR plus the back EMF. And back EMF, it is shown that is proportional to the angular velocity of the shaft. The faster the shaft spins, the bigger the back EMF would be. So we show it with a constant KE, back EMF constant, times the RPM of the shaft omega. Okay, so this is the relation that we have for the electric circuit. Now, as I said, we neglect induction. Otherwise, we have to add this term L di over dt, which is the voltage across an inductor. But since this L is typically very, very small, we neglect this term, and that brings down the order of the transfer function by 1. Typically, the order of transfer function for a DC motor is order 3, but with this simple thing, we bring it down to order 2. Now, the total torque for the motor is the torque that you put on the load to spin it, plus the portion that you waste on friction. Okay? Now, here, the difference between V and IR, if you bring IR to this side of the equation, it's going to be V minus IR equals what? Equals KE omega. This V minus IR is the actual voltage that is used for turning the shaft, okay? Because this portion of it is wasted. So that portion will never be used to generate torque, basically. So the difference between these two is the actual voltage that is applied and used for generating voltage. That here is shown by E, so we call that E. Okay, electromotive voltage. And clearly from here, that is equal to KE omega. Good so far? Now, here, to get an equation for the relation between torque and RPM, here we assume that for a moment that the friction torque is small, okay? We assume that the friction torque, which is the torque wasted between the commutator and the brush, this portion here, this is really small. If that's the case, then the power that we give to the motor is E times I. You know, in an electric circuit, E times I is the power. And the power that is coming out of the motor is the torque of it, the torque of the load, really, times omega. So if there is no friction in the system, or very small, P in and P out are the same. So EI is going to be the same as T omega. Good. Now, E was KE omega, so if I replace it down here, I get KE omega times I equals T omega. And if I get rid of 1 omega, you can see that the torque that is the torque of the load, the torque on the motor, is going to be KE times I. In most of the books, instead of KE times I, we show it by KT times I, and this KT, we call it the torque constant. But KE, this KE is what we call back EMF constant. And here, clearly, because torque was KE times I, as you can see from here, but we also say it's equal to K times KT times I, we can see that these two constants are the same. And if you look at the data sheet for DC motors, when it comes to showing torque constant and the back EMF constant, you're going to see the same number. Okay, so if you see KT and KE in different motors, they are the same number. Don't be surprised. That can be seen over here. They are the same values, okay? Now, what are these two parameters depend on? Or one parameter, really. What does this KT or KE depends on? Well, it depends on how the motor is made, okay? It depends on the construction, depends on the geometry of the motor, how many winding it has, correct? What material are used in it, and so on. The magnetic, the permanent magnet is made of what, and so on. So that depends on how the motor is made from what material. Okay? Now, there are other things too, of course. As I said, the dimension matters, the number of turns, as I said, and the magnetic flux density of the stator. So these are determining these values. Good? So let's move on. Up there, we have seen that V equals IR plus KE omega. That's what we had. Fine. We also found that here, we found that torque is equal to KT times I. So from here, I equals the torque divided by KT. That's what I'm going to use over here. For that I'm going to replace it by T over KT. Okay? And if I bring this term to this other side, I'm going to get V minus TKT over R is KE omega. Okay? So far, so good. And if I solve for omega, which is dividing both sides by KE, this is the formula that I get. This is the relation between the three important parameters: the shaft RPM, the rotor RPM, the voltage that I apply to the DC motor, and the torque that is applied to the shaft from the DC motor. So I can see the important relation between omega, V, and T. This is one of the most important formulas in a DC motor. And clearly, what does it say? If you look at it, it's a linear relation. It says that if I know the value of V and T, clearly I can find omega. Now, if I fix the value of V and just plot omega versus T, so my vertical axis is omega and my horizontal axis is torque, then omega is a linear function of time with a negative slope and with a y-intercept. So clearly, as you can see, they are basically these lines with negative slopes. And clearly, the bigger the V is, the bigger the y-intercept. So you see, as I move through bigger V's, my y-intercept, which we're going to call it omega no load, is going to go up. Yes? So the plot of speed versus torque for a DC motor is a negative slope line like this. And the bigger the voltage, the further out your line is going to go. Good. So now here we come up with a few terminologies. We say when there is no torque that the motor applies to anything. In other words, the shaft is rotating freely. So the shaft is rotating freely. There is no inertia. There is nothing that this motor is rotating. So I don't need any torque in this case, right? There is no load. So when torque is basically zero, there is no torque in this relation. Clearly, that is your maximum omega, because you can see that the effect of torque is negative. So if there is no torque, that is the maximum omega you can have, and we call it omega no load. Basically, this is when you just turn on a DC motor with no load on it and let it spin at voltage V. If you divide that voltage V by KE, that is going to be as fast as it can go. That is your maximum omega, and we call it omega no load, which is this point here, this intersection on the omega axis. Good. And the formula for it, you see, is V over KE. So this guy is called omega no load. On the other hand, the constant here that is multiplied by T, I'm going to give it a name. I'm going to call it Rm. So now I can write omega as omega no load minus Rm times T, which you can see over here. Fine? So at T of 0, omega equals omega no load. On the other hand, when omega is 0, what does omega of 0 means? Means you applied so much load on the shaft that it cannot spin. It comes to stop, which we call it stall, by the way. So stall is when the DC motor wants to spin, but it cannot. It is stuck for any reason, like you're applying too much torque, you're holding it, anything like that. That is called stall, and the torque for that is called the stall torque. How do you find it? You just solve for T here. Of course, it's going to be omega no load over Rm, and if you plug the Rm and omega no load over there, the simplification will be KTV over R. So you see the stall torque depends on the torque constant, depend on the voltage you apply, and depend on the resistance of the wire in the coils. So of course, if you apply bigger voltage to any DC motor, it is going to have a bigger stall torque, as you can see. So bigger voltage means bigger omega no load, means bigger torque stall. And torque stall is the maximum torque. Remember, torque stall is the maximum torque you can get out of any motor, and omega no load is the maximum omega you can get out of any motor. And of course, both of them will go up when voltage goes up, because with bigger voltage, you have more energy injected into the system. So if it spins freely, it can spin faster. If it stops, you need a lot more torque to stop it. So these two formulas are very important. The formula for omega no load, this one, and the formula for torque stall, and of course this original one, which is the formula for omega, V, and T. So these three are extremely important, and all of them are shown in this graph here. By the way, not only torque stall happens anytime that you're holding the shaft or the shaft cannot spin, like for instance, if you're drilling into the wall, correct? And the drill stops. Also, anytime you start from stop condition, so anytime you start your DC motor from a stop condition, it was in rest, at rest, and now you started, of course, you start from here, and then you move somewhere here, right? Depending on how much torque you need to move your load. So you start from here, you go there, and you stop right there. Okay, so you start in this initial point, and you go to this final point there. And at that point, depending on how much torque you need, you are going to get so much omega. So this is your torque operational. This is your omega operational, again, based on the voltage that you have applied. Clearly, the bigger torque you need, what does it mean? It means the smaller the omega, it can spin slower. The less torque that you need, it is going to spin faster. Okay, now what about power calculations? Well, power is T times omega. This is power out. And T is the total torque, the torque of the load plus torque of friction times omega. Again, for simplicity here, we neglect T of friction. So we say power is simply just the torque of the load times omega. And for omega, I'm going to replace it from this formula I just had here in 8. I'm going to replace it right here. Omega no load minus RMT. And if you plug in, you're going to get a linear function and you're going to get a quadratic function. So P as a function of torque is clearly a quadratic with a negative quadratic term. So this is your P, this is your T, and you clearly see the upside down parabola because of that negative sign, of course. Okay? And again, clearly, where power becomes zero, power is zero when omega is zero. So when omega is zero, power becomes zero, and omega zero means torque stall. So this is the torque stall point. And of course, you can see that the coefficients here are m and basically v over ke, right? This one, you clearly see this coefficient of the linear term does depend on v. And remember, what was Rm? Rm does not depend on v, but the linear term does. So clearly, when v goes bigger, by injecting more energy, you're going to get more power. And so you clearly can see that bigger v means bigger power curves. Okay? So this is your power curve. Now you might say, at what torque do I get the maximum power out of my motor? Where is this maximum point? For that, you need to take torque derivative of the power. So you need to take dp over dt equal to 0. And that's not a hard thing. This is a quadratic function. So clearly, if you look at that, that is going to be v over ke. That's the derivative of the linear term. And that guy is going to be negative 2rmt. If this is 0, clearly your torque is going to be v over 2k ERM. So this is where the power becomes maximum. If you need this much torque, then clearly you are at this maximum point. And if you plug this back into this formula, then you're going to get this part here. Look. Right? You see this term is multiplied by a v squared multiplied by rm. And if you simplify a little bit, you can find that the maximum power that you have is going to be ktv squared over 4ke r squared. And you see P max is proportional to v squared. So if you make your voltage 2 times bigger, you can get 4 times more power out of your motor here. Okay? So again, this P here, this P max is KT V squared over 4KER. And the location for it, this T was V over 2KERM. Okay, so this is your optimum point in terms of power. The next curve we're going to talk about is efficiency. So of course, you can always get more power out of a system if you injected more power. And that is exactly what you can see here. By injecting more power, I'm going to get more power out for sure. But where is the efficiency? You want to get to the point that a lot of the power that you inject is converted to torque and not a lot of it is used to overcome friction. So this is the part that in the efficiency part, we cannot neglect the friction anymore. These assumptions that we did back to back, here we cannot do it anymore. We have to bring that in and use it in our calculations. So before we look at these formulas, let me explain something. If you are pushing the motor with high torques, if you're asking for too much torque from the motor, torque means current, because remember, torque was kT times I. So large torque means large current through the rotor. And what does high current mean? High current means the power lost in the inductor An inductor is simply here the resistance of the rotor here, this portion. This is going to be too much because remember from electric circuits that the power loss in a resistor is Ri squared. So when I goes up with the power 2 of that, the heat is generated inside the resistor, okay? And that is not good. You're losing too much heat inside the windings. So you're going to drop efficiency. On the other hand, if you go to low torques means high omega, correct? We just learned that low torque means what? If you go up on this curve, low torque means high omega. What happens with high omega? Well, when omega is fast, then your friction terms are going to go up. Viscous friction, static friction, and so on, especially viscous frictions in the bearings and so on. They're going to start going up. So now your mechanical friction terms are going to get higher. And that also drops the efficiency. So ideally, efficient point is not when the torque is super high or it's super low. It's somewhere in the middle that there is a good balance between the energy in and the losses, the mechanical and the electrical ones. Now, where is that point? Let's go ahead and see if we can calculate something for it. So eta, the efficiency, is equal to the power out over the power in, of course. The power out is the torque that you put on the load times the omega of the shaft, and the power in is the voltage that you pass to the system times the current. Now, torque load is the total torque of the motor minus the friction torque. V, the voltage that you supply to the system, you can write it as R times IS. What is this? R here is the resistance, and I is I of the source. So this I is not I that goes through the winding. This is the current through the source, okay? So you can say that the total voltage of the source, voltage Vs, which is this one, this is equal to current passing through it times the resistance. So if I replace that right down here, your equations for eta becomes this. And now here, I'm going to replace my omega with the formula that I have up here. Look at this formula. I'm going to use this formula for omega based on V and T, and I'm going to replace it right down here. Okay, so this goes right there. Then what? The torque T motor is equal to KT times I. So that is going to go sit there. You're going to get this one. Now here is the interesting part. The torque due to friction can be modeled as KT times I no load. This is the interesting part. It says if there is no load on the system, the shaft is spinning freely, what happens? When there is no load, clearly torque load is equal to 0, so the total motor torque is equal to the friction torque. And this is equal to KT times I of the system, because torque motor is, as you can see, is KT times I. But which I? The I that is for no load condition, so I call it I no load. So this is the interesting part. The torque due to friction is KT times I no load. If you can measure I no load, then you can basically plug it right up here. So now you get this. Finally here, wherever I have KT, I'm going to replace it with KE because they are the same thing. So I replace all of these KETs with KE. Okay? And both of those KEs with this KE would be canceled out. So you're going to get to this. Now that you have this one, these two, they both share R. So that R and this would cancel out. You're going to get this one. And if you factor it out by dividing them by IIS, you finally get this equation in 15. So the final formula for eta is 1 minus I no load over I times 1 minus I over I S. Okay, this is all you have. And remember, I no load is definitely less than I, because I no load is the smallest current that you need. This is just to overcome friction. And since the T of friction is smaller than the total motor torque, I no load is less than I. So this whole thing is positive. And I is less than the total current through the source. So this one is also less than 1. So both of these parentheses are both positive. So eta is going to be positive, but how positive? Depending on these currents. If you can measure them, this is the formula for efficiency of a DC motor. And if you replace I in both of these with what? With T over KE or KT, clearly the function you will have is going to have a linear portion as well as a what we call a hyperbola function. So if you combine them, your curve for efficiency is going to look like this. Okay, it's not going to be a symmetric curve. It's going to be a little bit skewed to the left. But this is the summary of all different curves that you have, everything versus torque. And torque is the demand from your load. So here we have seen that the speed, omega, clearly drops versus torque. We have seen this one. We have seen that the power is a symmetric, basically parabola versus torque. We have seen that the efficiency is this kind of skewed curve. And of course, the current is what? The current is clearly linearly increasing with torque, because torque is K times I. Okay, so torque goes up, current goes up. So this is the most complete, I would say, graph that describes everything in a DC motor. This curve, I really like it. Now, if I want to know at which current I have maximum efficiency and where is my maximum efficiency, I have to take partial of eta with respect to I, set it to 0. I get this current. So the current at maximum for eta is square root of I no load times I of the source. And this maximum value, eta maximum, is going to be what you can see over here. 1 minus this square root, the whole thing squared. Okay, now, one thing we need to discuss is, where do you actually run a DC motor? Where do you want to run a DC motor? We call it nominal or operational conditions. Where do you suggest, as a manufacturer of the motor, where do you suggest to run the motor? At which torque? How much should we push a motor? Should we run it here, 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 here? Where? Where along this line, how much load do we put, how much torque load do we put on the motor? Where is it good to do it? Do we do it at the maximum power, or do we do it at the maximum efficiency? The matter of fact is, in most of the scenarios, the best desirable place to run a DC motor is between the max power and the max efficiency. This is the best place to run a DC motor. So if I want to show you, the best region to run any DC motor is between this point and this point. Okay, this range is the best range to run a DC motor, somewhere between the two. And you might say, why not operate it at maximum power? Why should we kind of stay here in the middle, not move too much to the right? I mean, too much to the left is good because you are more efficient, but it doesn't produce as much power as you want, right? Because if you are here, let's say, okay, your efficiency is relatively high, but your power is not as high as it could be. So you might say, why don't I come here, or even a little bit to the right of that? Yes, I lose some efficiency, but I get my power as high as possible, so I get the job done as fast as possible. Okay, so to me, time is more important than the price of electricity, correct? So what why don't I do there? Why don't I work there? The problem is overheating. Most of the DC motors are not designed to run continuously with high current levels, which means high torque. Okay, most DC motors are not designed to run them in a long time with a lot of current. They will ultimately overheat. They cannot dissipate all the heat generated in them because of friction and in the electric windings. They overheat, and ultimately you're going to see that, oh, my motor is all burned because it is heated so much, and the wires are burned, and guess what? I have to replace it. So even if you want to run a motor at high power relative to the max, make sure the time that you run is a short time. Don't keep running it. Give it some rest. Let it cool down. Okay, otherwise you're going to burn the windings very fast. Okay, so final thing we want to talk about is gearbox. Most of the motors, they come with gearboxes. Why? Because the motors typically run very fast. Their shafts run typically several thousand RPMs, and the torque that they generate at the no load is very, very minimum, right? Close to zero. But most of the time, we don't want to spin anything several thousand RPMs, and we want a significant torque so we can lift something, we can rotate something, we can rotate some gears that are meshed together and they are carrying something. So we need to reduce the RPM and bring up or boost the torque. For that, we can use a gearbox or gearhead, which are typically added at the end of any DC motor, right? Most of the time you see that there is some extra head that is added to the end of DC motor, and that is your gearbox. So when you see a DC motor, this is the motor, and this portion here is the gearbox that is added. And if you look inside of it, you're going to see a bunch of gears, and their goal is to bring down the RPM and bump up the torque. And if you see typically something here at the end of it, that is most of the time your encoder, which you use for servos. And we'll talk about that later when we go to servo motors. But typically this part here, the separate metal part here with these bolts and everything, that is your gearbox. Now, what's the effect of gearbox? The gearbox has a parameter called gearbox ratio or gear ratio, which is the input RPM over the output RPM. And typically, most of the time, this guy is bigger than 1, way bigger than 1. And the goal is, as you can see, is to bring down omega in by several factors to get to omega out. Okay, so clearly you see from here that omega out equals omega in over n. When n is bigger than 1, like 5, you bring down the RPM by 5. Now, the efficiency of a gearbox also has an efficiency. Okay, you might call it eta gearbox if you don't want to mix this eta with this DC motor eta. So the motor has its efficiency, the gearbox has an efficiency, and it depends on the gears you use, the lubrication, and so on and so forth. So a gearbox efficiency is the power out of the gearbox to the power into it. The in is coming from the DC motor, and the out is the one that you put on the shaft. Now, the power out is torque out, omega out. The power in is torque in, omega in, because they're all mechanical. And so from here, you can see that since this ratio here is 1 over n, if you cross multiply and simplify, you see that the torque out of a gearbox is the eta of the gearbox times the torque in times n. So if n is 5, what does it mean? If n is 5, means omega out is omega in over 5, 5 times smaller. Does it also mean that the torque out is 5 times torque in? No, because you need also the gearbox efficiency. So let's say it is 80%. What does it mean? It means torque out is 0.8 times 5 times torque in, which is going to be 4 times torque in. So clearly you get bigger torque, smaller RPM, but these numbers are not exactly the same because there is efficiency. And this efficiency actually itself does depend on the n. Okay? So depending on the n, your efficiency is going to be a different number. And these are coming in data sheets of DC motors. If you watched the video that I have for DC motors in robotics, I'm going to show you after this very fast. You can see I go over a data sheet and I read the numbers, these KT, like R, all of these important numbers. I show you where to get those. But as I mentioned, typically, if you have smaller gear reductions, the efficiency could be as high as 90%. But if you need a large reduction, you need a big N, your efficiency could drop to 50% and below. And again, it depends on what kind of gear head you're using. Is that a good expensive one, or is that a very simple one? So that is very important. So here is a sample data sheet of a DC motor from Pittman Amtech, and this is called DC054B series. And if you go down and look at this data sheet, many of the things that you need to know are provided here. So for instance, it says the maximum DC terminal voltage. This is your maximum voltage. It could be 80. You should never apply more than 80 volts to this. The maximum speed, omega max, that's omega no load, is 6,000 RPM. Okay? Continuous stall torque, that's your torque stall. How much is it? 0.071 Newton meter. So you see, you have omega no load, you have your maximum torque or stall torque. You have the maximum voltage you can possibly apply, because remember, you could apply different voltages, but up to certain limits. Then if you want to model the Coulombic friction torque, okay, TF, there is some value for it here. If you want to look at the viscous damping coefficient, which is from the bearings, there is a coefficient. We did not talk about that. The rotor inertia, which you need to model if you want to look at equations of motion, this is that. The weight of the motor is there, okay? All the dimensions for the motor are all given. And then when we go down, there is more. So here you can see that, for instance, for rated voltage 2, which is 12 volts, this is how much voltage I want to apply nominally. And the torque that I really want to expect out of this is about 49,000 Newton meters. The rated speed I really want to spin this guy at is about 3,600, 3,700. If I apply a higher voltage to this motor, 15.2, now I can expect to get what? I can expect to get a little bit higher RPM. Okay? And of course comes with higher RPM, a little bit smaller torque, although the voltage is higher. If you want the torque constant, look at that, 0.0263. Now here is the part I said. Voltage constant, KE, that's your back EMF constant. Look at KT, look at KE, look at them. They are both the same number. Do you see that? KT and KE are the exact same number. And then terminal resistance, that's your R value, 0.72 ohms. And then look at inductance, 0.63. And you said, well, didn't you say that the inductance is much smaller than resistance and so on? But these two numbers are very close to each other, aren't they? The problem is this guy, millihenry. So that is 0.63 times 10 to the negative 3. So you see, your inductance is more than 1,000 times smaller than your resistance. That's why if you neglect that inductance, you have not really done a very bad approximation. Okay, so these are the data sheets that you can see for common DC motors, and there is more and more of that. You can see these curves that I showed you. Remember the curves? This is your current here. This one that goes down is your speed, and this one here is clearly your what? This is basically, you call it the maximum continuous torque. Okay, remember I said you don't want to run these motors for continuous time, for a long time. When you run them for a long time, then you can run the system at lower values, really. Okay, you cannot expect it to give you so much torque for a continuous time, so you have to have smaller torque values, and that is called continuous one. So these numbers that you see, these beautiful curves, are not meant for continuous operation. Under continuous operation, you have to use smaller values. Okay, you have to clearly use smaller values, and that is where this curve telling you that if you want to operate, you cannot operate all over this chart. You should only operate within the blue region. Otherwise, you are going to overheat the wires and you're going to burn it. So hopefully this was useful to you. You learn something about DC motors, their theory and everything, and I'm going to see you in the next lecture. Thank you.